Welcome back to the deep dive. We're continuing our journey into renewable energy.
And today we're really getting into the weeds, so to speak, looking at how plants actually work.
Exactly. We're focusing specifically on Lecture 5 from Professor Supriya Ghosh's 2021 course at ICT Mumbai Renewable Energy Resources, GTT 2105.
Right, this builds directly on our last deep dive, which covered Lecture 4. And Professor Ghosh's lectures, there are 15 in total. They're just packed with detail.
They really are. So our goal today is to get a handle on how plants capture light and, turn it into energy and building blocks, the basics of biomass, really.
We'll be diving into photosynthesis, efficiency, even some surprising plant strategies.
Yeah, should be some aha moments connecting biology to energy. And just a reminder, if this really sparks your interest, the full lecture from Professor Ghosh is on YouTube. We'll link it in the show notes.
Definitely worth checking out for the full picture.
Yeah.
So Professor Ghosh starts Lecture 5 by reminding us about the photosynthetic setup in leaves.
Right, the light harvesting systems.
Exactly. He points out there are two main ones, photosystem I and photosystem II, and they absorb light slightly differently.
One around 700 nanometers, the other 680 nanometers.
That's it. And it's crucial, like Professor Ghosh says, to remember longer wavelengths mean lower energy.
So the 680 system is grabbing slightly higher energy light.
Correct. And both systems generate these, well, high-energy chemical products. It's biological energy storage, not like, plugging something in.
Very different from a battery or electricity grid, yeah. This initial capture using two systems, it sort of hints at nature maximizing things, doesn't it?
Absolutely. It's about capturing a wider slice of the available light. Okay, so let's look at photosystem 2 first.
Okay.
When light hits a compound like chlorophyll, its electrons get excited. They jump to a higher energy state.
Professor Ghosh had that analogy right. If you just dissolve chlorophyll in water,
Yeah, and shine light on it, nothing much really happens in terms of storing that energy.
the electron just falls back down, maybe releases some heat or fluorescence.
Exactly. Wasted energy, basically.
But plants have figured out how to stop that. This is where it gets really cool,
It really is. The moment that electron gets excited, it's like it's instantly swept away.
creating a charge separation, right? Positive and negative are pulled apart.
Precisely. This spatial separation stops them from just recombining immediately. Professor Ghosh really emphasizes how incredibly sophisticated this is.
And how hard it is to replicate efficiently in our own, artificial solar cells.
Definitely. So you've got this electron whisked away. What's left behind is a hole, effectively a positive charge.
Which is looking for an electron.
It's highly oxidizing, yeah. And this is where a manganese-containing enzyme comes in.
Okay.
It uses these electron holes to basically rip apart water molecules.
Releasing oxygen, the oxygen we breathe.
That's the one, a byproduct for the plant, essential for us.
So what happens to that electron that got swept away?
It goes on a journey, like a relay race, passed down a chain of different molecules.
The electron transport chain.
Exactly. Each molecule gets reduced, then oxidized as it passes the electron along. And as it moves, the electron gradually loses some energy.
Okay, losing energy, but where does that energy go?
Good question. This is the key energy conversion step. The electron's energy is used to convert ADP, adenosine diphosphate,
A low energy battery.
right, into ATP, adenosine triphosphate.
The charged battery, the plant's energy currency.
That's it. It happens with the help of hydrogen ions and phosphate. So light energy is now stored chemical energy in ATP. Remarkable efficiency.
Wow. Okay, so that's photosystem 2. What about photosystem 1?
It works in a similar way. Absorbs light, excites an electron.
But where does its replacement electron come from?
It comes from the electron that just finished its journey from photosystem 2.
Ah, okay. So the electron that already gave up some energy to make ATP now fills the hole in photosystem 1.
Correct. And the electron that gets excited in photosystem 1, it also goes through its own shorter relay race.
Leading.
Eventually, it reaches a molecule called NADP plus condostiana, nicotinamide adenine dinucleotide phosphate.
Right.
With help from protons, this high-energy electron reduces NADP plus to NADPH.
Which is another energy carrier.
Exactly. It's both an energy source and a reducing agent. It can donate electrons for building things later.
Okay, so let's recap this light part. The plant takes sunlight and water,
Uses two photosystems, separates charge, splits water,
releasing oxygen,
and creates ATP, the energy currency.
and NADPH, the reducing power, and another energy store.
You got it. That's the essence of the light-dependent reactions.
Incredible. So what happens next? Professor Ghosh moves to the dark cycle.
Yeah, the Kelvin cycle. It's called dark, not because it needs darkness, but because it doesn't directly use light.
It uses the products from the light reactions, the ATP and NADPH.
Exactly. This is where the plant takes carbon dioxide from the air and actually builds sugars.
And Professor Ghosh stresses the role of enzymes here, right?
Mhm.
Making these reactions happen easily.
Absolutely. Especially the famous one, Rubisco. It makes converting CO2 into sugar seem effortless, biologically speaking.
So how does this cycle start?
It starts with a 5-carbon molecule, ribulose bisphosphate,
Yeah.
RuBP.
Ah.
3 molecules of RuBP react with 3 molecules of CO2, and Rubisco makes this happen.
3 5-carbon plus 3 1-carbon.
Gives you 6 molecules of a 3-carbon compound, 3-phosphoglycerate, or 3-PGA. Nice carbon math, as Professor Ghosh points out.
And does that step need energy?
Interestingly, no. RuBP is already energetic enough for that initial reaction.
Huh. Okay, so we have 6 molecules of this 3-PGA.
Right. Now, the next step needs energy. Converting 3-PGA into another 3-carbon molecule, glyceraldehyde 3-phosphate, or G3P.
And this is where the ATP and NADPH come in.
Precisely. 6 ATP get used up, releasing energy, becoming ADP again. And 6 NADPH get used, providing electrons, becoming NADP plus again.
They get spent here to build the sugar precursor.
Exactly. Professor Ghosh mentions ATP gives about 7.3 kilocalories per mole, so using 6 gives a significant energy boost.
And this 3-PGA, the first stable product, that's why it's called the C3 cycle.
That's the one. Kelvin's Nobel Prize work identified this as the first stable intermediate, hence C3 photosynthesis.
Got it. So we now have 6 molecules of this G3P. What happens with those?
Here's more cleverness. One of those 6 G3P molecules is siphoned off. That's the net output, which can be used to make glucose, fructose, other sugars.
Okay, so one G3P is the profit, basically.
Kind of, yeah. The other 5 G3P molecules, they go through a series of reactions to regenerate the original 3 molecules of RuBP.
So the cycle can start all over again.
Exactly. But regenerating the RuBP also costs energy.
More ATP.
Yep. Another 3 ATP molecules are converted to ADP in that regeneration phase.
Wow. So total investment for one G3P output?
Professor Ghosh sums it up. 9 ATP and 6 NADPH are needed to make 1 G3P.
And G3P is half a glucose.
Right. So to make a whole glucose molecule from 6 CO2s, you need double that. 18 ATP and 12 NADPH.
That's a significant biological energy cost. It really shows how much energy is captured from light initially.
It really does. And all this Kelvin cycle chemistry happens in the stroma, that fluid-filled space inside the chloroplast.
Right, separate from the light reactions in the thylakoid membranes. Okay, Professor Ghosh also briefly touched on the structures of ATP and NADPH, didn't he?
He did, just to give a feel for how they work. ATP and ADP share the same core adenosine part. The difference is the phosphates.
Diphosphate for ADP, triphosphate for ATP.
Exactly. Adding that third phosphate using solar energy makes ATP the higher energy form, like loading a spring.
And NADP plus versus NADPH.
The key change is in a specific ring structure, a pyridine derivative. When NADP plus gets reduced to NADPH, gaining electrons and a proton, the aromatic nature of that ring is broken.
And that structural change makes NADPH.
A good reducing agent. It's ready to donate those hydrogens and electrons back to something else.
But making NADPH isn't spontaneous, right? Professor Ghosh mentioned that.
Correct. Thermodynamically, it takes energy. Delta G is positive.
So the energy comes from
the high-energy electrons from photosystem I. Sunlight provides the push needed to create NADPH. Both ATP and NADPH synthesis ultimately depend on that captured solar energy.
It all comes back to the sun. Okay, let's revisit Rubisco for a second.
Yeah, that key enzyme. Professor Ghosh highlights its high affinity for CO2.
Which makes the first step of the Kelvin cycle efficient, even with relatively low CO2 in the air.
Exactly. Around 300, 400 ppm, it still works well, but there's a catch.
Ah, the oxygen problem.
Yes. Rubisco isn't perfectly specific. It can also react with oxygen.
Which leads to photorespiration.
Right. Under high oxygen, low CO2 conditions, Rubisco can grab an oxygen molecule instead of CO2. This starts a process that actually breaks down RuBP and releases CO2. It wastes energy.
Working against photosynthesis.
Pretty much. He mentions the warbird effect from 1920 showing higher oxygen slows photosynthesis down.
And the implication, over millions of years, as oxygen built up in the atmosphere.
The overall rate of photosynthesis might have actually decreased, kind of counterintuitive.
But now, with CO2 levels rising,
and maybe oxygen slightly decreasing in some places, perhaps photosynthesis could increase again, if there are enough plants, that is.
Underscores the importance of plant life, for sure. So plants have evolved ways around this photorespiration issue.
Some have. This leads us to C4 photosynthesis, which Professor Ghosh introduces. Things sugarcane, maize, many grasses.
Okay, what's different in C4?
It's basically a CO2 concentrating mechanism. It evolved often in hotter, drier climates where photorespiration is a bigger problem.
How does it concentrate CO2?
Instead of Rubisco grabbing CO2 first in the main leaf cells, mesophyll cells, another enzyme, PP carboxylase, does the initial capture.
And PP carboxylase doesn't react with oxygen.
Nope, it's highly specific for CO2, or bicarbonate technically. It forms a 4-carbon molecule, oxaloacetate. That's why it's called C4.
Okay, 4 carbons. Then what?
This oxaloacetate is converted to another 4-carbon molecule, usually malate. And this malate is then transported
Transported where?
to specialized cells deeper in the leaf, called bundle sheath cells. These cells are where the C4 plant keeps most of its Rubisco and runs the Calvin cycle.
Ah, so it's physically separating the initial CO2 capture from the Calvin cycle.
Exactly. Inside the bundle sheath cells, the malate releases its captured CO2.
Creating a really high concentration of CO2 right where Rubisco is located.
Precisely. It effectively swamps Rubisco with CO2, minimizing the chance of it grabbing oxygen and starting photorespiration.
Clever. What happens to the rest of the malate molecule?
It becomes a 3-carbon molecule, pyruvate, which gets shipped back to the mesophyll cells.
To be reused.
Yep, gets converted back into PP, using some ATP energy, ready to grab another CO2. It's a cycle layered on top of the Calvin cycle.
So C4 takes extra energy using that ATP to run the concentrating pump, basically.
It does. But the payoff is much higher efficiency, especially in high light and high temperatures where C3 plants struggle with photorespiration. Professor Ghosh notes their specific leaf anatomy helps too.
The bundle sheath cells surrounded by mesophyll cells,
Right.
like a dedicated compartment.
Right. Very effective adaptation.
Fascinating. And there's another adaptation too, SAM.
Yes, crassulacean acid metabolism. Think cacti, succulents, desert plants.
Okay, how do they handle things? Water conservation must be key.
Absolutely. SAM is like C4, but separated in time instead of space.
Separated in time. How?
These plants do something remarkable. They only open their stomata, the leaf pores, for gas exchange at night.
When it's cooler and less water will evaporate.
Exactly. So at night, they take in CO2 and fix it using PP carboxylase, just like C4 plants, making malic acid.
And they store this malic acid.
Yes, store it overnight in their cell vacuoles, banking CO2.
Okay, then what happens during the day?
During the day, they keep their stomata tightly shut to save water, but they have sunlight.
So the light reactions run, making ATP and NADPH.
Correct. And now, during the day, they break down that stored malic acid.
Releasing the CO2 internally?
Right inside the cells, where Rubisco and the Calvin cycle enzymes are waiting, they get a concentrated CO2 supply, fed by the nighttime storage.
Wow, so they run the Calvin cycle during the day using sunlight energy and internally release CO2, all while keeping their pores closed to save water.
It's an incredibly effective strategy for surviving in extremely dry environments. Temporal separation of CO2 capture and fixation.
Okay, let's try and wrap our heads around all this. Professor Ghosh's lecture, Lecture 5, it really unpacks photosynthesis beautifully.
Yeah, from the basic light capture, making ATP and NADPH,
To the Calvin cycle building sugars using Rubisco.
and then these amazing adaptations like C4 and CAM, overcoming limitations like photorespiration and water loss. Plants are just incredible chemists.
And for you, the learner, understanding this foundation is just so crucial for appreciating biomass energy.
Absolutely. How plants fix carbon, how efficient they are in different conditions, even their structure, it all matters for how we use biomass sustainably.
Which we'll definitely get into more as we continue through Professor Ghosh's lectures.
Right. Hopefully this deep dive gives a clearer view of the amazing biological engines driving this renewable resource. Nature solutions are often the most elegant, aren't they?
They really are. And again, check out the full lecture linked in the show notes for even more depth.
So next time, we'll build on this. We'll look at how this biomass, once created, gets converted into usable energy forms.
Following Professor Ghosh's lectures,
Yeah.
should be equally fascinating connecting the biology to the applications.
Definitely. And maybe something to think about until then. Given all this complexity and efficiency in photosynthesis,
Yeah.
what kind of bio-inspired ideas could we maybe use to develop totally new renewable energy technologies, drawing inspiration directly from these natural processes?
That's a great thought to leave folks with. Lots to chew on there. Thanks for joining us on the deep dive.